Today's webinar is the sixth in a series regarding the Highway Safety Manual presented by the Florida Department of Transportation. Today's webinar regards the Highway Safety Manual's Part C, Chapter 12 on urban and suburban arterials. Good morning, my name is Jack Freeman and welcome to this webinar training. I am a senior principal with Kittleson & Associates in Orlando, Florida. My contact information is shown on this slide, and please feel free to contact me individually after this webinar with any questions we have not sufficiently answered during the course of this webinar. This is the sixth of 9 webinars. The previously conducted webinars can be found on the FDOT Office of Safety website. The next webinar will be conducted on Thursday, November the 3rd. The learning objectives of today's webinar are shown here. And similar to what we've done in other webinars, we will be reviewing the safety performance functions and looking at those, and you'll find that those to be greatly expanded as we move into Chapter 12. We'll also talk somewhat about crash severity distributions and how the NCHRP 1738 spreadsheet can help you with this analysis. Crash modification factors will be reviewed. And this again will be somewhat different with Chapter 12. We'll go through some example applications and then we'll talk about upcoming changes to the Highway Safety Manual, but with particular regard to Chapter 12. As we've noted before in previous webinars, we will be focusing the training on the use of the NCHRP 1738 spreadsheet. Therefore, the participants should be comfortable in using Microsoft Excel. But before we get started, we'd like to do a few poll questions to get a little background on the audience we have today. So the first question is, please state the organization type where you work. And there are 5 different choices provided. The second question is, what technical area do you primarily work in? And again, there are 5 different choices provided. Third question is, state your past experience in using the Highway Safety Manual, ranging from I've never used the Highway Safety Manual to I could teach this course and you could take my job. The last question is, do you have access to the Highway Safety Manual? And these range from yes, and you have your own personal copy, or no, and you may not have even an HSM within your office. Today's webinar is focused on Chapter 12, the urban and suburban arterials from Part C of the Highway Safety Manual. This is the third of 5 webinars we have and will be conducting regarding Part C predictive chapters. The next 2 webinars are regarding new chapters 18 and 19 on freeways and ramps. The Part C introduction provides information with regards to crash predictive methods. The prediction is based upon facility type, ADT, and various geometric elements. Crash severity can be predicted. Chapter 12 encompasses crash prediction methods for segments of urban and suburban arterials and intersections along them. You will find these analysis procedures to be more complex than what you've previously seen in Chapters 10 and 11. Historically, we've had to speculate about safety instead of being able to quantify it. And with the Highway Safety Manual, this really removes the subjectivity from design decisions. We don't have to make statements such as, this won't be safe any longer. We can actually go through and use the Highway Safety Manual to quantify the safety decisions just like other project decisions. For years, we've been able to do things like 2.65 acres of wetlands are impacted, or delay decreases from X to Y using Highway Capacity Manual procedures. Now with the Highway Safety Manual, we can say 11.8 crashes per year are expected to be eliminated by making this improvement. The relationship between crashes and volumes is nonlinear, so the use of crash rates can be misleading, and let's look at an example in the next slide. Here you'll see, shown in blue, a safety performance function, and it is nonlinear. And to get you oriented on the graph, the bottom or the x-axis is average annual daily traffic, and the y-axis or to the left is crashes per year. The green line represents the average crash rate, and it is a linear function increasing as average annual daily traffic increases. You can also see the red point, which is the historical crash data for the facility. So as you look at this, the question should be, should we target this location for safety improvements? And you're seeing historic crash data that is above the safety performance function, so that you're seeing what we would expect for this type of facility, and the crash rate is actually higher. So yes, this should be location should be targeted for safety improvements. The Highway Safety Manual is an AASHTO publication and must be purchased from them. It is available in hard copy or a single user PDF. For FDOT staff, Central Office will be providing guidance to access the Highway Safety Manual electronically. All other resources are available for download from the websites shown on this slide. So I'd like to have another poll question to gain a little bit more knowledge on your use of the HSM. The question is, which of the following predictive methods are you most likely to use for your job? Chapter 10, Chapter 11, Chapter 12, or equally for all three. So as we continue with the overview of Part C and particularly Chapter 12, first of all, we'd like to talk a little bit about, and you've seen this with previous webinars, homogeneous facilities, and being able to go through and develop those homogeneous segments throughout the project, and being able to look at it intersection segment, and being able to do that. And this really doesn't change from what we've previously done in chapters 10 and 11. Based upon different types of facility changes or lane changes, we still need to go through and develop those homogeneous segments. We'll also take a refresher of what's the difference between urban and suburban and rural, and we'll talk about that in just a few minutes. And then we'll get into a heavy focus on SPFs, CMFs, the calibration factors, and talk a little bit about empirical bays as we go through the analysis portion of this webinar. So as a refresher, the HSM does provide guidance on urban, suburban versus rural. And there's often questions about, do I apply Chapter 10 rural two-lane highway, or do I apply Chapter 12 urban, suburban on a two-lane road? Well, the guidance in the HSM is limited, but it does state, and it does follow the FHWA guidance, that an urban roadway and an urban facility is placed inside urban boundaries where the population is greater than 5,000. Rural are areas outside urban boundaries with population less than 5,000. And suburban is really not defined, but is lying between the two. What is often used is the FDOT urban area buffer maps, and these are available on the FDOT site. They show those areas, and the definition of suburban or transition areas is 1 mile beyond the urban boundary, and then you're into rural. So I often use this as good guidance when I'm trying to make that decision about whether I should use an urban or a rural type of analysis. The urban and suburban arterial has certain subscripts, no different than what we've seen before, but it's just much more expanded. The typical roadway segment equation subscripts are shown here. We have 5 different facility types here, ranging from 2-lane undivided arterials all the way up to a 5-lane section with a 2-way left turn lane. So we have 5 different facility types for segments. We also have 4 different facility types for intersections. 2 3-legged, stop control and signalized, and 2 4-legged, again stop controlled and signalized. And the stop control is only for the minor street only. There is no 6-lane segment or intersection analysis procedure at this time, but as I'll talk about at the end of this webinar, that is forthcoming. So another question for you is, what is the HSM subscript for a 4-leg stop control intersection? So as I previously noted, there are 5 different segment facility types and different models or SPFs developed for each of these. And they all have different ranges showing here. They can go from 0 to 32,000 in the case of a 2-lane undivided arterial, all the way up to 0 to 66,000 for a 4-lane divided facility. When you start getting out of those ranges, the model really weren't not developed for these higher ranges, so the applicability of the model becomes questionable, and you should use your own engineering judgment in applying the model. So before we move on, I'd like to do another poll question, and the question is, what is the maximum number of lanes of an arterial that can be analyzed with the Chapter 12 Urban and Suburban Arterial Method? And there are 4 different choices. They are 4 lanes, 5 lanes, 6 lanes, and 8 lanes. The urban and suburban arterial method is the same in concept as the previous chapters, just much more involved. For starters, there are 5 crash types included in the segment crash type prediction. They are multiple vehicle segment crashes, multiple vehicle driveway crashes, single vehicle segment crashes, vehicle-pedestrian crashes, and vehicle-bicycle crashes. And as we go through this, each of these have their own separate safety performance functions and safety performance function calculations. Let's see how this looks in an equation. And the model does look a little different. You can see here that what we have is a motor vehicle component, which is the SPF times crash modification factors for those particular SPFs, and then models for pedestrians and bicyclists. As we further break this down on the next slide, we start to see that the SPF for the motor vehicle component has the 3 different components I just spoke about. These are multiple vehicle crashes, single vehicle crashes, and multiple vehicle driveway crashes, shown there in the subset below. So as we look at these and the different components of this, we'll go through the analysis procedures looking at what these are for multiple vehicle crashes, single vehicle crashes, and driveway crashes to go through there, but they all total up to become that overall motor vehicle component for that, and then you apply the crash modification factors to the sum of these 3 different crash types. So the crash modification factors for this, there are 5 different crash modification factors. You can see the base conditions, and as we go through this, there are some particular things that you might want to note, and I would suggest that you read the Highway Safety Manual with regards to this, particularly roadside fixed objects. It talks about in there that they cannot be, they should be larger than 4 inches in diameter. They should not be breakaway. And then I'll give you an example for a fence. If it's a continual longitudinal type of object, it gets broken up into 70-foot segments. So each 70-foot segment constitutes an object. So you need to go through and read the details of the Highway Safety Manual to understand this. The same thing with median width. When you have divided roadways, you need to look at that. It does not pertain to when you have 2-way left turn lanes. It does not pertain to when you have median barrier. It needs to be a traversable median that you can have and apply this. So you need to read the details of the Highway Safety Manual to understand the applicability of these different crash modification factors. Let's look at graphically the different types of SPFs that we have. The first is the multiple vehicle non-driveway collisions and the SPF for that. It's very similar to what we saw previously in Chapter 11. It has an A and a B factor. These are taken from the table. In this case is Table 12-3. It also has average annual daily traffic, and it has the length in miles. And these become parts of it. And you can notice that there are 5 different graphs here. Again, along the bottom axis, the AADT, or average annual daily traffic, and along the y-axis on the left side are the predicted average crash frequency per mile. And you can see how this varies for the different types of facilities. You can see the 4D, or 4-lane divided, is on the bottom, having the lowest crash prediction frequency. The 5T is on the top, being a 5-lane with 2-way left turn lane, being the highest crash frequency prediction. As we move on, we look at other types of facilities, or other types of crashes, I should say, such as single vehicle crashes. Again, the same type of model, A plus B, again taken from a table, average annual daily traffic and length. And the graph looks the same, with the exception of, you can see that it's much fewer crashes for single vehicles. It's 1, 2, and 3. Previously, we were going up to 20 and 30 on the y-axis. So it's much fewer crashes for single vehicle crashes. And you'll note that as we go through the different examples. And the coefficients used in here are taken from Table 12.5 of the Highway Safety Manual. And the SPF for the multi-vehicle driveway crashes is an equation. As you go through it, it is based upon the different driveway types. And we'll talk about the driveway types in the next slide, but you have different models for each different arterial type, different models for each driveway type, or different coefficients, I should say. And you go through the analysis multiple times depending upon the number of driveways that you have. In the next slide, it shows all the different driveway types. 7 basic types. Major and minor is broken into, major is defined as that driveway serving 50 or more parking spaces. Minor is that driveway serving less than 50 parking spaces. So that's the division point, and it obviously will require some engineering judgment as you go through it, but it also breaks it down into commercial, industrial, or industrial/institutional, and residential. Again, you need to go look at the Highway Safety Manual to be able to get the details. We provided some of those details here in this slide, such as industrial, institutional serves factories, warehouses, schools, etc. Another SPF in the overall Chapter 12 is that for vehicle-pedestrian crash, and you use a pedestrian crash adjustment factor. This is really a function of N sub BR, which is the total crashes you just did for the motor vehicle component. So this is the total from that times a pedestrian crash adjustment factor. You will notice in the table 12-8 on the right-hand side of the slide, it's divided by posted speed, it being 30 miles per hour or lower or greater than 30 miles per hour, and you have 2 different factors. One of the few places in the Highway Safety Manual that we actually consider speed. But this is really a one-size-fits-all model. Doesn't account for pedestrian volumes or pedestrian facilities along the roadway segment. The next adjustment, or SPF, is for vehicle to bicycle crashes, and there's an adjustment factor for this as well. Similar to vehicle pedestrian, we use the N sub BR, the total predicted crashes for the motor vehicle component, times a bicycle adjustment factor. Again, this is divided similar to the pedestrian one for posted speeds of 30 miles per hour or lower or greater than 30 miles per hour. And again, similar to the pedestrian, it doesn't account for bike volumes or bike facilities being present along the roadway segment. Okay. So as we look at the base conditions for the crash modification factors supporting the urban and suburban segment models, again, you'll have the 5 here shown. On-street parking not present, no roadside fixed objects, and the median width being 15 feet. Depending upon the facility type that you have, it may not be applicable. For instance, in the 2-lane, it won't be applicable. And then looking at lighting and automated speed enforcements are the different crash modification factors for the segment models. Also, we have calibration factors, and Florida DOT developed crash modification factors for the 5 different facility types that we have, and we'll be applying these as we go through the different examples. But these are available for you through the FDOT Plans Preparation Manual, and on the website. This is table 23.5.3 of the PPM. Okay, let's go through and summarize the process that we have gone through and discussed for estimating the total predicted segment crashes. As shown here, it's a 6-step process, starting with the base prediction for the multiple vehicle crashes that include multiple vehicle non-driveway and multiple vehicle driveway, plus the base prediction for single vehicle crashes. We then apply the crash modification factors to the vehicle crashes only. We apply the calibration factor at this point, and then we go through and estimate the pedestrian crashes and estimate the bicycle crashes and sum all this up for the total. So let's look at an example. And what we want to do is do the basic calculation steps and show you and demonstrate to you those basic calculation steps as we go through it. And then we'll follow that immediately on using the NCHRP 1738 spreadsheet to demonstrate how it's done in the spreadsheet. And for simplicity in this example, we're going to assume no historical crash data and no EB data analysis will be done, or empirical Bayes analysis will be done. So for example 6A, we have a 4-lane divided arterial. You can see that we have shown SPF inputs being average annual daily traffic of 23,500 vehicles per day, a segment length, the number of driveways, and in this case all are major commercial driveways, and also posted speed. And again, the posted speed is in there to be able to go through and use your vehicle to pedestrian and vehicle to bicycle crashes and do that analysis. For your crash modification factors, you've got several listed here. 3 are changed from the base conditions. We have the roadside fixed objects at 20 per mile being 15-foot offset, the median width of 20 feet, and also road segment lighting is present. And we have also added in the Florida calibration factor for the 4-lane divided roadway of 1.63. So let's walk through that base vehicle prediction and demonstrate to you by hand how this is done so you can gain a further understanding. Again, the base motor vehicle part of the SPF is the sum of motor vehicle non-driveway crashes, single vehicle crashes, and driveway crashes, as is demonstrated in the formula at the top of the slide. Looking at that motor vehicle non-driveway crashes, you can go through and see the different factors that we do. The A and B is taken from table 12-3. We were given the average annual daily traffic of 23,500, and the length is 0.5 miles or half a mile. And we go through the calculation to determine the N predicted for multiple vehicle non-driveway crashes to be 1.925. We do a similar type calculation for single vehicle crashes, and again pull the coefficients. Different table is 12-5, but still the same average annual daily traffic and length to go through that calculation of 0.363. And you will note, as I discussed earlier, that it's a substantial reduction for single vehicle than for multi-vehicle, which makes logical sense. The final calculation is going through for multiple vehicle driveway crashes and being able to do that calculation. We use average annual daily traffic of 23,500. The number of driveways is the small n sub j. and that goes in there. And then there is a driveway related collisions that comes from table 12-7, and you pull that coefficient out of that table. In this case it is 0.033, and you go through the calculation to get the number of driveway related crashes. In this case it is 0.271. So all of this gets added up, and you can apply the crash modification factors to this. So the crash modification factors are shown on the next slide. You can see those here. We have 3 that are varying from base condition, and so you can see slight adjustments in those coming from different formulas and calculations that are shown in the Highway Safety Manual, and the combined CMF of these, again, these are multiplicative, and so it would be 0.91 would be the combined CMF of these 5 different crash modification factors. So let's look at the overall total here and see what we have for motor vehicle related crashes. And it is shown here. We've taken this out in detail to show you how it's done for motor vehicle, non-driveway, single vehicle, and driveway crashes. You can see where we've applied the calibration factor of 1.63. We've applied the combined crash modification factor of 0.91, and we get, when it's all added up, 3.795 crashes per year. The next step is to calculate the predicted pedestrian and bicycle crashes. And we go through and we use that N sub BR, the motor vehicle predicted crashes, times a factor that comes out of different tables in the Highway Safety Manual. For the pedestrian related crashes, it comes out of table 12-8, and for the bike crashes it comes out of table 12-9. And you can see those factors listed here times the overall sum of motor vehicle related crashes, and it's a simple multiplication to develop those crashes. For the PEDs it is 0.72 crashes per year. For bikes it is 0.019 crashes per year. So now we need to calculate the total predicted crashes, which is simply the sum of the motor vehicle crashes, the pedestrian crashes, and the bicycle crashes. You can see that all stated here, and that total in predicted for all the different facility types is 3.886 crashes per year. So you can see as we step through this process, it's a bit more complicated than what we've done previously in chapters 10 and 11. But as we move to the spreadsheet, it's pretty much the same in applying the spreadsheet for chapters 10 and 11, and it greatly simplifies this calculation. But we wanted to show you the different steps that you have to go through to be able to do it. So what you see is the chapter 12 spreadsheet here. We've gone in and we're under segment 1, so we click on tab for segment 1, and it looks very similar to what you've seen in the past for chapters 10 and 11. You go through here, and again, the blue are different pull down type menus, and you basically enter the data off from those pull downs, and the gold or yellow is where you have to actually enter information or data. We go through, and this is a 4-lane divided roadway, so we pull down on the 4D, and we enter that information in. We go through and enter in your segment length, your average annual daily traffic. We don't have any on-road parking or on-street parking. We enter in, we have a 4-lane divided roadway, so we must enter in the median width, and then we go through and enter in different other factors such as lighting, it being present, speed enforcement not being present, the number of driveways. You can see there's an entry cell for each of the types of driveways you have. In this case we have 5 commercial driveways, so we need to enter that number in there, and that's entered in. We go down to the bottom and we see a speed category for greater than 30 miles per hour. We have a 45 mile per hour posted speed along here, so we're using that, and we enter that. And then at the very bottom we enter in the roadside fixed objects and the offset for those objects, and then we enter in the calibration factor. So all this is entered in, and the spreadsheet goes through and calculates the end predicted. And next slide will show that the end predicted is 3.9. Under column 2 total, you'll see 3.9 is that value. The previous calculation was that we went through by hand was 3.886, so it checks, and we know that we've got a good value. But you don't have to do that check manually. We just wanted to demonstrate that as part of this training. So let's move to a different example, and we'll call this example 6B, which regards a Suburban 5-lane arterial. And we made some changes in this overall parameters that you see here. Again, we have SPF inputs, and we will always show the average annual daily traffic and also the segment length, because those are functions of all the SPFs we do. The driveways, we have 11 minor commercial and 1 major commercial, so we've listed that. Posted speed, again, is needed for that vehicle to bicycle and vehicle to pedestrian SPF calculations. The crash modification factors have changed a little bit too. You'll notice there is no median listed here, and that's because with the 5-lane arterial we have a 2-way left turn lane, so the median crash modification factor does not apply. And you'll also notice we've put in the 5-lane calibration factor for Florida of 0.70. So we're going to go directly to the spreadsheet this time and show you that. And we've entered these factors into the spreadsheet. Again, I don't need to restate these, but you can see how they've been entered in. The 5T is a pull-down menu. We've entered in the length and average annual daily traffic. We've gone through and entered in the some of the crash modification factor information, as well as the commercial driveways. You can see we've 1 for major and 11 for minor, and then gone down to the roadside fixed objects and the speed and the calibration factor, and gone through and entered all those inputs for the spreadsheet to make the calculation. Okay, so let's look at the results that we have from the input of that data. And as you look under column 2 of worksheet 1L, you'll see that the total end predicted is 4.4 for this calculation. And this is important for us to use as we go through and evaluate and compare to other alternatives. And what we'd like to do is now test some certain countermeasures and see what happens if we want to make some improvements to this roadway. So we got 2 examples. One is 6C, where we consolidate the driveways. We are actually taking part of the minor commercial. We had previously 11. We're reducing that down to 5. And we're making 1 additional major commercial, increasing that from 1 to 2. So we now have a total of 2 major commercial and 5 minor commercial driveways. Example 6D is we would convert the 5-lane arterial with 2-way left turn lane to a 4-lane divided arterial. We would provide a 10-foot wide median, and we would keep the number of driveways that we had originally in example 6B. So let's go through these steps and look at the different results. First of all, let's look at our example 6C spreadsheet inputs. And first one is, I want to emphasize, save your results from example 6B. Save your results and then go through and make the modifications, because most of this data doesn't change. In this case, the only thing you're changing is 2 cells. You're going through and changing the minor or major commercial and minor commercial driveways. And you're making those, and you can see those, the red arrows where they are. We've changed them to 2 and 5. Everything else stays the same. And we can go through and do that calculation and make that calculation, and we can see that again, if you go under in worksheet 1L, go to column 2, you can see that in predicted, and it for the total is 4.1. So we have had a reduction in total crashes as a result of the driveway consolidation from 4.4 to 4.1 as making that driveway change. Now we'll do example 6D and go through and do that. And again, it's save the spreadsheet and make the changes that we need in there. So there are several changes. All have been flagged here by red arrows. We've gone from a 5T type of facility or roadway type to a 4D, 4-lane divided. So you need to scroll down and make those changes. You need to go back to the major and minor driveways and change those back to 1 and 11 as we had in the original example of 6B. And then we need to change the calibration factor because we've gone to a new facility type. You now need to change the calibration factor, and that is 1.63. We go through this calculation, and with the replacement of the two-way left turn lane with the wider median, we've had a reduction in crashes from 4.4 to 4.1. You can see that in again in column 2 under total, where you see the 4.1. But I'd like to point out that the calibration factors are greatly influencing these results. You may recall previously when I showed you the SPF graphs, the difference between 5T and 4D and the great differential you had there. Well, we've got calibration factors that are 0.70 for the 5T and 1.63 for the 4D. So this brings these numbers together very closely as a result of these calibration factors, but you should apply them because they are applicable to Florida. So let's look at the overall summary here in the results summary. And let me go back and remind you what 6B, 6C, and 6D stand for and what they are. Well, 6B is the 5-lane with two-way left turn lane. 6C was keeping it 5-lane with two-way left turn lane and going through driveway consolidation. And 6D was a 5-lane to 4-lane divided conversion and going back to with 10-foot wide median and going back to the number of driveways we had in 6B. And you can see the comparative results here, just summarizing here. So overall, what we're seeing is that as we go to 6C and 6D, we have some improvement. And looking at some overall improvement there, again, as we look at 6D, the calibration factor is having a bit of an effect on what we're seeing there, but it is a number that you should apply as we go through and do the analysis. I'd like to point out also that if you have crash data, you should be applying that to this, and you should go through the EB analysis. Due to the time frames of this webinar, we're not getting into the EB analysis with this particular example. We'll show that in a minute, but you should go ahead and apply crash data to get a more robust and a better type of analysis. So I'd also like to point out, taking a closer look at the results that you have and being able to use the spreadsheets and then walking through the spreadsheets to basically see what types of results are you getting. And there's a couple here that we'd like to point out regarding CMFs, the frequency of crashes at for single vehicle, etc., the crash types and what are we getting from severity distributions, and looking at those different types. These are all available through the spreadsheets. We just want to point it out so that you can use this understanding to develop more effective countermeasures and look at the countermeasure effectiveness as you're evaluating different types of improvements for this roadway. So let's take a closer look at crash modification factors, and what we'll use is the crash modification factors table from example 6B, which is again the 5-lane two-way left turn example. And you can see that, point out that the median width crash modification factor CMF is 1.00 because we have a two-way left turn lane. And you can also see that the only real CMF that we have is for the roadside fixed objects 1.01. So the combined CMF, when you multiply everything out, is 1.01. With making the changes for driveways, the driveways, if you will recall, are all under safety performance functions. So they modify safety performance functions. They do not affect the overall crash modification factors. So this would stay the same. But then when we get to example 6D, and we go to 4-lane divided, and we now have a median, we would have to go through and show that, and that would change the median because of a 10-foot wide median, and we would get a CMF there of 1.01. So let's take look at some of the results that are coming out of the 1738 spreadsheets. These are all still under segment 1 tab. They're just following down, and you see now we're looking at worksheet 1C, which is for the multi-vehicle non-driveway. And if you go all the way to the right, you'll see the blue highlighted area of in-predicted. It will show you that in-predicted. Again, this is example 6B. It's the in-predicted for the 5-lane with 2-way left turn lane. And you're able to go out there and see that in-predicted for non-driveway. Down at the bottom is going through and looking at the collisions and different types of information regarding collisions. How many of those crashes are rear end collisions? And if you go to the far right hand column, you will see that 1.74 of those crashes are rear end crashes. So approximately 2/3 of the crashes are rear end crashes that you're having for multi-vehicle non-driveway crashes. So we can go through and do this type of comparison for each of our different alternatives, and being able to look at that for each of the alternatives. Again, because we're only doing driveway consolidation for 6C, it will be the same and will not change anything from what we previously had in 6B, because we have only done non-driveway crashes here. So we're seeing that overall, what we're seeing here is that the non-driveway crashes for the 4-lane divided alternative is higher, primarily due to the calibration factors and the difference between the 0.7 for 5T and the 1.63 for the 4D. Looking at further into the details here, we go down under the same tab as segment 1 to single vehicle. And again, you can see to the right the end predicted for single vehicle of 0.467. And you can see, again, there's a breakdown, but the collision types are a little different this time. You're looking at collision with animal, collision with fixed object. So it's giving you, and these are generic numbers that come out. They're really default numbers from national data. So use these, with a little bit of caution, because they're not directly applicable to Florida, but they'll give you a good rule of thumb, as you go through the analysis and try different types of countermeasures. So again, doing the same comparison for single vehicle, and going through that, you will see the comparison between 6B, or the 5-lane with 2-way left turn lane, a little bit higher than the 4D. Again, calibration differences, noted that in the past, but you'll see a slight reduction for the 4-lane divided facility. Going further down the spreadsheet, we can now look at the multi-vehicle driveway, which is shown in worksheet 1G, still under the same segment 1 tab, and you will see the driveway types all shown in the left-hand corner of the highlighted cells, showing the major commercial, minor commercial. We've entered in 1 driveway for the major commercial, 11 for the minor commercial, and you can see the resulted crashes that we get for those driveways. And then it totals down in worksheet 1H, showing the total crashes to be 1.313 for the overall driveway crashes, and this again is for example 6B. We can go through and do similar type analysis, compare those in 6C and 6D, and look at those, and you can see here that the multi-vehicle driveway crashes for the 5T under example 6B is considerably higher than the 4-lane divided alternative, which you would expect, because you have better access control, and you would expect this. And so this, even with the calibration factor differences, you are seeing the results you would expect regarding driveway crashes. So now let's look in a little bit more detail what the spreadsheet provides us for pedestrian and bicycles. On the top is the pedestrian, down is the bicycle crashes, and these are taking the proportional differences, and they're using the predicted times the factors coming out of the tables, and going through and calculating that out. Want to note though that you've already applied the calibration factor in developing the predicted for the motor vehicle. So when you see in column 7 the calibration factor is 1.0, that is because it's already been applied previously. And if you make it different than 1.0, it will be double counting the calibration factor. So that should always be 1.0 for the pedestrian and bicycle crashes. So I'd also like to point out, using example 6B, the severity distributions that are available in the spreadsheets. This is again under the segment 1 tab. It's further down, worksheet 1K, and it shows the different types of severities that you can obtain for multi-vehicle and single vehicle, looking at different types of crashes or collisions with animals, etc. This is an overall aggregate summary of what you're seeing there. So it's again a good tool as you want to go through and look at analysis and look at this. Again, it's based upon default type distributions and not Florida data, but you can look at it, and it gives you a good feel for the crash types you could expect. So now let's move into the urban, suburban, arterial intersection models. And as you can see, there's 4 different models here. 2 for the 3-legged intersections, 1 stop control, 1 signalized, and again 2 for the 4-legged, again being stop control and signalized intersections. And you can see we also have upper volume limits on these, shown here on this slide. A good guide for you to follow. The spreadsheets will not allow you to enter in values higher than what's in the upper limits of this. So you can enter it into the spreadsheet, but if you have volumes that are higher, and these are the 2 approaches that you have coming in for the major and 2 approaches you have for the minor for the 4-legged, you add those together in daily traffic. As with the segment models, we can go through and calculate total crashes based upon 4 different types. Multi-vehicle crashes, single vehicle crashes, vehicle-pedestrian crashes, and vehicle-bicycle crashes. Obviously, you would not have driveway crashes for the intersection model, so that does drop out. The model for the urban, suburban, arterial intersections is a bit different than what you've seen previously in chapters 10 and 11, but is very similar to what we just saw for the segments. It goes through and it does look at the N sub BI for multi-vehicle and single vehicle crashes. It goes through and it looks at pedestrians. It goes through and looks at bicycles. So that is all brought together and multiplied by the calibration factor as shown in the top equation. The N sub BI again is looking at that SPF and times the calibration factor. That's your motor vehicle component as you go through this overall calculation. Looking at the model even further, you see that N sub SPF highlighted in blue gets broke down into multi-vehicle crashes and single vehicle crashes and becomes that overall sum of those 2 crash types. The equations for The multi-vehicle crashes and the single vehicle crashes are shown here in this slide. Again, it's a function of average annual daily traffic for both the major approach and the minor approach. And going through using coefficients that come out of tables in the Highway Safety Manual, you can go through and calculate and use this SPF to calculate the predicted crashes for multi-vehicles and single vehicles. The CMFs for vehicle crashes are shown here, and these are the intersection CMFs, 6 different types of crash modification factors, considering left turn lanes, right turn lanes, signal phasing, right turn on red, roadway lighting. And I'd like to point out that roadway lighting and intersection lighting is in every single segment and intersection for chapters 10, 11, and 12. And the important part of that is why you're seeing in the Manual of Uniform Traffic Studies, Chapter 14 on lighting justification says use the Highway Safety Manual prediction methods. This is why lighting is in every single one of these, and you can use that analysis process. So let's look at the SPFs for vehicle-to-pedestrian crashes and go through this calculation. A bit different than what we saw for the segment, a bit more complex. It has a PED base equation. You can see that here. And it also has crash modification factors for the PED collisions. So let's talk about, first of all, the PED base equation. It considers in the average annual daily traffic for it looks at the total. It looks at at minor approach and major approach. It also has a PED volume, and that PED volume is the daily volume for all crossings. So you need to look at daily volume for all crossings at that intersection. And it's also the number of lanes crossed. And I'll go through those, show you a little demonstration of that in just a minute as to how you come up with that N number of lanes for this. But it also includes crash modification factors. Number of bus stops within 1,000 feet. Number of schools within 1,000 feet of the intersection. Number of alcohol sales establishments within 1,000 feet of the intersection. Okay, and the Highway Safety Manual goes through and defines any place that sells alcohol as an alcohol sales establishment. A grocery store selling alcohol is an alcohol sales establishment. A convenience store selling alcohol is that alcohol sales establishment. So you will have, and need to go through and get that data as you go through the inventory. This slide shows you the how do we go through that calculation of the maximum number of lanes crossed by a pedestrian. And it is actually active lanes that you cross here. This shows the demonstration here. If you look at the bottom part where you see, say north is up, you have a median there. The median is not an active lane. So you've got 2 and 2. So you have a refuge there. It is along the 2 major roadway approaches. We can call it east and west in this case. Both of those are 6 lanes. Turn lanes do count. So in this particular case, it would be, 6 lanes would be the maximum number of lanes crossed by a pedestrian in the crosswalk. The vehicle-to-bicycle collisions is very similar to what we previously looked at for the vehicle-bike collisions for a segment. It is basically that total overall N sub BR, which is the motor vehicle in predicted, times a bike factor. And the only difference in this table and what you saw before is because intersections typically don't have to worry about speeds. We do not have the breakdown between less than 30 miles an hour and greater than 30 miles per hour. It's just a factor based upon the intersection type, and you multiply that by the overall N predicted for the motor vehicle component. So I'd like to have a question now, and a little polling question. Been a while since we've had one. So which of the following affects the frequency of pedestrian crashes at intersections on urban and suburban arterials per the HSM? and you've got 4 different opportunities to choose. And this is, I want to emphasize intersections. It is presence, absence of crosswalks, the type of intersection, do you have pedestrian countdown signals, and posted speed limit. FDOT has recently updated and provided urban and suburban intersection calibration factors. They are shown here, and they are also available in the FDOT Plans Preparation Manual, Chapter 23. Let's look at an example of a 3-legged signalized intersection. You can see that here, and with crosswalks on a couple of approaches. And let's go through the analysis of this intersection. Here's the data for it. And we'll call this example 6E. Again, it's signalized. We have the minor and major approaches at average annual daily traffic. We have the daily PED volume of 15. The maximum number of lanes crossed by a pedestrian are 4. And then we go through and provide in the crash modification factor inputs. 2 left turn lanes. We do have protected permitted on the major street. So that's, those 2 are basically differences from the base condition, and everything else is base condition information. We do not have any bus stops, schools, or alcohol sales establishments within 1,000 feet, and we're using the current FDOT calibration factor for this analysis. We input this data into the spreadsheet. You can see here, and we've gone through with a 3SG, and we are showing, the average annual daily traffic, lighting not present. We've entered the calibration factor. Since it is a signalized, we drop down to data for signalized intersections only, and we enter in the appropriate information there. We have the number of approaches with left turn lanes is 2. It really doesn't matter what approaches are on. It's just 2 in this particular case. And we go ahead and enter in the number of approaches with signal phasing. We enter in, protected permitted for the major, protected for the minor, and then go through and enter in the data with regards to pedestrian crossing volumes, number of lanes crossed, and the data that we need for the pedestrian vehicle crashes of, and you have to basically go through and enter that data in. If it's 0, you need to enter in 0 to make sure it's in there for bus stops, schools, and also alcohol establishments. So you go through that calculation. This is what the worksheet shows. It comes out and gives you a total of crashes, an in predicted of 6.4 crashes per year. What I'd like to do now is go in and talk a little bit about EB and a little bit about that as we're getting toward the end of this webinar. The data you need to enter into the analysis is based upon the number of single vehicle and the number of multi-vehicle crashes that you have, and going through that type of analysis. So as you evaluate the data, your historic crash data, you need to really get into the details. Is it a single vehicle crash or a multi-vehicle crash? And you've looked at it over several years, and in this particular case, you have no single vehicle crashes, and you have an average of 2.4 multi-vehicle crashes per year. You go to that urban site web tab and be able to click on that, and you'll see this particular spreadsheet, very similar to what we've done before with empirical Bayes. You'll just notice that you also have the division between multi-vehicle and single vehicle crashes, and you actually can enter that in there. Or if you don't have it, you can go to the project, the urban project totals tab, and enter it in, total crashes at the bottom. But the better you break this down, the more refined data you'll get as you go through the analysis process. And you'll see the results coming up, shown over in blue, highlighted here, and you get a adjusted crash frequency you had previously predicted under column 2 of 6.3. It is now, you look in column 5, and it is 4.0, and that's your unexpected value of having entered in observed crashes. Let's look at another example. We'll call this one 6F, and this is to use the same intersection, but now we've got a new development coming in on the south end of this, and they want to add a fourth leg to this intersection. So we want to analyze what does that do to crashes by adding this fourth leg into the intersection. So now let's look at changes in the information for this example as a result of adding in that fourth leg. You'll notice that the average annual daily traffic at the minor approach is slightly increased due to the new development. The changes in configuration at the south end is increased the maximum number of lanes crossed by a pedestrian to 5. The left turn lanes, we now have left turn lanes on all 4 approaches, so that's gone to 4. And you'll also notice that the calibration factor has changed because now we've gone from a 3-legged intersection to a 4-legged intersection, so that calibration factor had to be adjusted. And we go through and we also make these changes in the spreadsheet, changing it to a 4SG type of intersection type. We increased the minor street volumes. We changed the calibration factor, the number of approaches, and we go through and add in, we've added in protected permissive on both approaches on the major street, and we've made both left turns on the minor street being permissive, and gone through and made those adjustments to be able to calculate a new end predicted for this intersection. And you can see that in the next slide under total column 2, and it's increased pretty significantly up to 8.2. So we previously went through the analysis and provided empirical base, but now we've gone to a 4-lane intersection, and we don't have crash data for a 4-lane condition, and so but we do have data for a 3-leg condition. Let me pose this question to you. Suppose crash data is available for the 3-leg as we had in example 6E, and when analyzing a future condition with the 4th leg in place, should empirical Bayes analysis and going to unexpected be used? Yes or no? So we got some changes on the horizon with regards to Chapter 12. In fact, what you'll see here, but let me give you an update. This research has been completed to go through and add in 6-lane and 8-lane 2-way arterials and also 1-way arterials. And I'll talk more about that in a minute, but first the update. Chapter 12 will be rewritten as part of the new Highway Safety Manual 2nd edition. But the research is complete. It is being final balloted now and should be forthcoming either in late 2016 or out in 2017. So keep on the horizon, look at that just like chapters 18 and 19 are now available. We'll have those in future webinars. This will be coming available to the profession. So what does it contain? It contains expanded information. Now we will have 6-lane undivided, 6-lane divided, 6-lane or 7-lane, 6-lane with a 2-way left turn lane or 7 lanes, and even an 8-lane divided. We'll also have, for the first time, 1-way arterials, and looking at 1-way arterials, 2, 3, and 4-lane 1-way, and we go through the same basic types of calculations that we just talked about. Multi-vehicle, single vehicle, vehicle-pedestrian, etc. in doing that. And crash modification factors for segments has also changed a little bit. We now have lane width. We didn't have lane width before. We now have shoulder width. We now had median width. We still have it, but we've added in median barrier. Previously, with median barrier was there, we had a crash modification factor of 1. We also have railroad highway crossing. And if there's a crossing along the segment, we'd go through the analysis there. And then we also go through the driveways, and we have roadside fixed objects as we had before. Looking at the intersection predictive models, these are also been expanded a little bit. They now will cover all the 6 and 8 lane conditions, but the same basic 3-leg, 4-leg, signalized, unsignalized intersections, and also for the first time we'll have one-way street intersection predictive models, and go through that and look at things for 3-legged and 4-legged unsignalized intersections and signalized intersections on one-way streets. Again, it's the multi-vehicle, single vehicle, vehicle, pedestrian, vehicle, bike type of calculations that we've previously done and demonstrated in this webinar. So, what are some of the Chapter 12 limitations? Well, there are no SPFs for all-way stop control. And there's nothing for roundabouts, although this research is underway at this time too, and will be included in the second edition of the Highway Safety Manual. It's not applicable to interchange areas. You have to use the interchange in Chapter 18, 19 types of analysis there. There's no model underway yet for one-way or 6 lanes or more, but that should be forthcoming probably within the next year, so you'll have that available to you very shortly. So now I'd like to go live to answer any questions you've submitted during the webinar and open it up to any additional questions beyond that. Thank you for your time and I appreciate your listening.